Okay, so this video is about how to visualize fractals in an easy way of in Wolfram Mathematica. So the code being shown here is already uploaded on GitHub, and you can find from the link in the video description. And to use the file, you just open it and use enable dynamics. And but the point of doing this is not to demonstrate any complicated programming skill, but to show you how to make easy use very simple code to show some interactive visualization of for fractals, and you can make it more complicated. And feel free to make a pull request so that we could make this worksheet better. And the first function, the function that made it useful is that it's the manipulate function, which takes a bunch of expressions and interactive objects, and with the range of the object in which you could manipulate on. So this means that I want to manipulate n from 1 to 4 by 1, so that you also end up in an integer. Otherwise, it doesn't work. So we could so first set of visualization is function of curves. So you could observe those curves are made up by simple line segments. For example, Koch curves is one line segment, and turn left one line segment, turn right by 2 times the angle, 120 degree, and then one line segment to the left, one line segment. The Hilbert curve start with this. So these are the 3 line segments to start with. And similarly, you get piano curves and Minkowski curves, and they are essentially all 1D line segments, because the lines the lines are always 1D topological objects. But if you start to iterate, let's go from 1 to 2. And you can see that each of the for the Koch curve, each one line segment is iterated, and it's substituted by this product itself. So if you look closely, you actually get if you take one part of the new object and compare with the original object, you get this form is self-similar, because this part of the object is the same as the original. It is similar to the original object, but by the different level of iteration. But you can imagine what would happen if the iteration level goes to infinity. You could eventually get a rather complicated object. But that's not very surprising for the snow. For the Koch curve, and if you look at the snowflake, you get similar patterns. What's interesting is that by iteration, it can actually get a different fractal dimension, so that its fractal dimension it's different than it's not equal to its topological dimension. So for the rest of the for the other 3 curves, you could see that by this iteration, it slowly fills up the space. So that's why people call them space filling curves. So when people say curves, it doesn't it sometimes mean that this geometric object is smooth, but in this way it means that if you get several line segments and you could iterate and take the limit close to infinity, they also call it a curve. So there's a lot more geometric stuff lying and the line in the Mathematica analysis. You have to get a series to actually rigorously prove that it's got different it's got a fractal dimension not equal to its topological dimension. So that's a contradiction, that although this object is made of lines from line segments, so small bit of one 1D object, it can fill up the space, not quite the space. What you get is still rational points, but you could for arbitrary points for example in this square, you could get one part of this curve that's arbitrarily close just by iterations. And similarly, by substitutions, you could also have 2D meshes or 3D meshes goes from that goes from that goes from one very simple object to a very complicated object by iterations. For example, this is the Mender mesh, which has the property that each time every square is substituted by substituted by eight smaller squares and whole. So by this iteration, its error ceases as the iteration goes. So although the geometric object is made of square, its error converges to 0 by iteration, because its timing every time its error is timed by 8/9. Similarly, you could drill those holes on 3D objects, and each cube is substituted by, I don't know, 8 plus 8 plus 4, which is 20 smaller cubes. And you can see that by iteration, but by increasing the level of iteration, the volume doesn't converge to non-zero. It doesn't converge to a non-zero number. So similarly, you could have the Sierpinski mesh in 2D and Sierpinski triangles. Sorry, they call it Sierpinski pyramids in 3D, and Cantor mesh, or people call it Cantor dust in 2D. All right, so I've only made very few of these, but I hope you could discover more fractals with the functionality given by Mathematica, and use this useful function called manipulate to create interactive visualization, which is hopefully intuitive. Thank you.